In this video, I will try to take you step by step through expansion of a determinant of a transition graph in terms of its traces or walks on the graph itself. So what you see on the left now is a graph, and it has 7 nodes, which means we have partitioned our state space into 7 regions. And then there are lines connecting them. And we are assuming that from each region there are 2 distinct ways of getting to the next region. And we mark that by full line, symbolic dynamics 1, and dotted line, symbolic dynamics 0, meaning, for example, that from here to there we just stretch, or that's a full line, no, dotted line, or we stretch and flip, that's a full line. So a walk on the graph is just any closed loop on the graph. So for example, what are the walks of length 1? Well, I can start on this node and I can go around. That's one walk, and it has a weight which we call T0, a little trace. It means just the product of the links. In this case, it's only one link. Then there's another walk of the length 1, it's this one. And that we call T1. Then there is only one walk of the length 2, and that's this one here. So far we have found 2 cycles of length 1. It's this one. That's this one here, with a weight T0, little trace. And then this one, T1. So these are cycles of length 1. Which means that when we write our determinant of 1 minus Ct, we'll get 1 minus 2 cycles of length 1. Then there is 1 cycle of length 2, this guy here, or this guy here, which has a name T01. So when we look at the cycles of length 2, there will be a term which will be this one, this cycle. But then we have to take products of all the shorter cycle, and these 2, T0 and T1, show up as products. And as each little trace carries a minus with it, this show up as a relative minus sign. We have now accounted for cycles of length 1 and length 2. What about cycles of length 3? Well, here is one. Or write it separately. This is this one. Little trace 0, 0, 1. We went through dotted, dotted, full, so that's 0, 0, 1. But there's another cycle of length 3. It's this one, or this one, which we can write it T0, 1, 1, because they're 2 full lines. And so when we start finding these contributions, 1 minus 0, we get T0, 0, 1 plus T0, 1, 1. These are these 2 guys. But then there'll be a cycle of length 3, this thing here, multiplying these ones. They have no points in common. So that will give me a relative sign T0, and then there'll be T0, 1. Or I can take this one and this one. That's minus, this is this is T1, T0, 1. I interchange the 2. And that's all I can do at length 3. Be gone. What about cycles of length 4? Well, here is one cycle of length 4. Tuk, 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 tuk. 1, 2, 3, 4. I went through 4 nodes. 2 of them were dotted lines, it's 0, 0, and 2 of them were full line, it's 1, 1. And for reasons I don't remember, I'm keeping some old cycles here. There is another cycle of length 4. It's this one. This cycle here. And that one has a weight T0, 1, 1, 1. How about cycles of length 5? Well, it gets a little bit funky, but here is 1. I start here, go, go, go. It's directed, so I choose this, and I have only way I can go here, I can go there, and I come back. That's this cycle here. And that's 2 zeros, tuk tuk, 2 ones, tuk tuk, a 0 and a 1, and then I go periodically on. And here is another cycle of length 5. I start here, 0, 0, 0, 1, 0, 1, 1. So this is T 0, 0, 1, 0, 1, 1. Then there is a cycle of length 7. Pretty funky. I start here, I go there, I go around, go through 0. Then there is a 1, 1, 1. So there are 3 of those guys drawn here. Tuk, 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 tuk. So this is T 0, 0, 1, 0, 1, 1. As you can see, for a large graph, you better leave this process of generating walks to computer. Pretty soon these things get out of hand, the graphs don't look planar, you can't really draw them by hand, but you get the drift of it. You simply go until you run out of cycles. And it turns out there is another length 7 cycle. So I start here, I go around, I go around, I go here, 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 and here. And that's a cycle whose little trace is T 0, 0, 1, 1, 1, 0, 1. And thanks God we stop at this point. We can't find any more cycles. Now, you can, of course, try to draw other walks on the graph. Here is an example of such a walk. You can decide you go here, you come back, you go here, you do something, you go here, you go here, you do something, you go here, you go here, you go here, etc. And finally, you find a closed loop of a long cycle. But this is a self-intersecting. And we have learned that if you have a cycle that's self-intersecting, so you go through all kinds of sites here, and at some point you come back, it'll always show up in combination where you do this separately minus this separately. So if you have something whose symbolic dynamics is A, which is some sequence of A's and zeros, times TB, if they have a node in common, so they're intersecting, there'll always be a combination called TAB, which is all the itinerary of A followed by B. And this combination, for counting purposes, is 0. So that's exact shadowing. So this process of finding self-intersecting cycles always stops at some point. And now we have a complete expression for the determinant as a loop expansion. I apologize for the messy, busy graph, but what we have found out is that there are 12 cycles. They go up to period 1. So we found cycle length 1, 2 of them, cycle length 2, 2 cycles of length 3, 2 cycles of length 4, a cycle of length 5, cycle of length 6, 2 of them, and then we found 2 cycles of length 7, and nothing longer that's not self-intersecting. And now we combine all these things in either the cycles, for example, these are the fixed points. So here are the fundamental cycles showing up in the expansion. Or the combinations of shorter cycle that don't intersect each other, like this one and this one. And they show up with relative minus sign. And we account for all the products of shorter cycles which have no points in common. So here are examples of various such things. So this you have to do privately in a quiet room yourself. But the result of this is that you get a finite determinant of this shape organized by cycle lengths. And if you're trying to find eigenvalues of t, so if you're trying to find this, according to the Cayley's theorem, this determinant has a 0 whenever z is inverse eigenvalue. So you solve the problem that equals 1 zt. But that's just roots of polynomials. And this polynomial is written explicitly here. So this is the fundamental structure of a Markov graph that has 7 partitions. And what happens in periodic orbit theory, this is the basic object, what I've written down here. But in periodic orbit theory, there will be also so-called shadowing corrections. And that's what we will learn when we go from transition graphs to Perron-Frobenius graphs or traces of evolution operators. They'll have this structure plus corrections.